All right, so I wanted to discuss dimensional analysis, which is relevant for the power counting. So I think what I did was I said little d is the number of, we're going to go to 4 dimensions, but little d is space-time dimensions. And capital D is the operator. Dimension. So in a field theory, what you're calculating is a path integral. I'll just call it phi, but okay, it includes scalars and gauge fields and fermions. But it's an exponential of the action. And so the action, which is the integral, okay, so this is why locality comes in. We assume that the action is some integral of a local Lagrange density. And because it's in the exponent, this has better be dimensionless. And I like putting big square brackets, so this is just means the dimension of S. So the dimension of S is 0. And I'll count dimensions in energy units. And then because integral d to the d has dimensions, energy dimensions minus little d, the Lagrangian has to have the same dimensions as the space-time dimension. So the dimensions of the fields are fixed from the kinetic energy term. So you have d mu phi squared is the scalar kinetic energy term. So it has 2 factors of fields and 2 derivatives. And each derivative counts as 1. So the dimension of a scalar field is the space-time dimension minus 2 divided by 2. Just because there are 2 fields in here and the subtraction of 2 is for the 2 derivatives. For fermions, this is d minus 1 over 2 because the fermion Lagrangian, the Dirac action has only 1 derivative in it. This is psi bar d slash psi. The gauge field, F mu nu has a derivative, so it looks just like the bosonic case. So gauge fields have dimension d minus 2 over 2. And a covariant derivative is d plus IgA mu. So GA has to have the same dimension as a derivative so that you can add them together. And so a gauge coupling constant has dimension 4 minus d over 2. And of course, a normal derivative, just an ordinary derivative or a covariant derivative, has dimension 1. And you can use this to calculate the power counting for operators in arbitrary space-time dimension. But in the interest of time, I'll now just set little d equals 4. And then scalars have dimension 1. Fermions have dimension 3/2. Gauge bosons have dimension 1. And gauge coupling constants are dimensionless. So now we can go back to the Lagrangian and ask, what are the operators of any given dimension? So this first case is operator of dimension 0. And the only operator you can have of dimension 0 is the unit operator, just a number, 1. And the coefficient of this is the cosmological constant. So that's the constant term in the Lagrangian. Then at dimension 1, well, you can't have a derivative because there's nothing, the derivative has to act on something. And so the only operator you can have at dimension 1 is a field. So you could have basically a linear term in the scalar potential. And usually what you do is you shift phi by some constant, basically, to get rid of the linear term in the potential. Remove it. Or like in the standard model where the scalar field is the Higgs has a hypercharge, and a term linear in the Higgs field would not be gauge invariant. You would need at least H dagger H. So typically, this term is not so interesting. At d equals 2, you have phi squared. And I'm just going to treat phi like a generic field. So a complex scalar field you can think of as two real scalar fields. So by phi squared, I include phi star phi or phi squared or whatever. So this is a scalar mass term. And that's there. Then at d equals 3, well, you could try writing something like d mu phi, for example, but that's not Lorentz invariant. So you can't do that. Then at d equals 3, you can have phi cubed. You can have a fermion mass term. At d equals 4, there's phi fourth. There's a Yukawa coupling. There are the kinetic terms, fermion, scalar, and gauge field. And so on. Now, when you start writing these things down, you could, for example, have had an operator which was like d squared phi, which would be dimension 3 in your Lagrangian. Now, if you have something like d squared phi, that's just the integral of d mu phi, and that's 0. Neglect, as long as you're not doing some stuff with topological terms or anomalies and so on. And I'm going to ignore that we don't have time to discuss that here. So except in very special cases, typically, any term which is a total derivative, you can remove. So you can also remove d mu phi, something like this, which is the same with 0, which is the integral of d mu phi squared plus phi d squared phi. So I might have thought that at dimension 4, I had two operators from the scalar, the first one and the second one, but the sum of the two is a total derivative and is 0, so I can ignore, I don't need this second operator here. I can replace it by the first one with a minus sign. So when you write down the Lagrangians, the one thing people call IBP, which is integration by parts identities, or the same thing, the integral of a total derivative is 0. So you can remove some operators just because they're total derivatives, basically. And the second thing you can do is you can make field redefinitions, which I discussed at the beginning. For example, phi goes to phi plus phi cubed over m squared. Now, if you're working up to dimension 4, typically, I'll see this a little bit later, these are not useful because what happens when you start making definitions like this is you're mixing an operator of dimension 1 with an operator of dimension 3. You can see that with the explicit 1 over m squared in the denominator. So if I take any of these operators and make a field redefinition, I'm going to get something with a 1 over m squared in the denominator and a new operator which is 2 dimensions higher than the one I started with. So all of these things will go, dimension 2 will give me a shift of dimension 4, this one will be dimension 5, that one will be dimension 6. And if you're doing what's called a renormalizable theory, so historically what was called a renormalizable theory was you only had operators with dimension d less than or equal to the space-time dimension. So in our case, less than or equal to 4. You don't want to make field redefinitions like this because you're going to introduce operators whose dimension exceeds 4. But in an EFT, where you are allowed arbitrary high dimension operators, this field redefinition will be useful. Okay. So, yeah, I already mentioned that, a trivial field, well, sort of an implicit field redefinition which people use without talking about it is to make the kinetic energy diagonal, where basically phi I is becoming some matrix times phi. You're just making a linear transformation. So you're not changing the dimensions of operators, and then it reshuffles flavor indices and makes the kinetic energy diagonal. Okay, so my Lagrangian will be a sum of terms where the dimension is less than or equal to 4. This is what was usually, this is if you want the what's called the renormalizable part, or the renormalizable Lagrangian. And then in an EFT, you can have L d equals 5, d equals 6, and so on. And by dimensional counting, the Lagrangian has to have dimension 4. So the dimension 5 terms have some power of something in the denominator, which I'm going to call m. And this will be m squared, et cetera. And m is what's sometimes called the power counting parameter, or the EFT scale, or the new physics scale, or whatever. And the EFT is a systematic expansion in inverse powers of this m. And this is called the power counting expansion, or the 1 over m expansion for the EFT. And this is why, if you want to make a field redefinition consistent with the EFT, like here, the field redefinition will have the same m in there as in this expansion, so that you maintain the power counting for this. And what's going to happen is that you're going to shift. You're going to get shifts in dimension 6 proportional to dimension 4 coefficients times 1 over m squared, and shifts in dimension 7 proportional to dimension 5 coefficients times 1 over m squared, et cetera, by this kind of change of variables. And maybe I can give a little problem to work out where you can see how you can eliminate certain operators this way. So the first non-trivial results come in at dimension 6, where you can get rid of certain dimension 6 coefficients by making field redefinitions like this. And for SMEFT, it took like, I forget, 30 years or something for this story to be done correctly, because Buchmuller and Wheeler, I think around 1984 or something, first wrote down the SMEFT operators. And it turned out that there were various field redefinitions to remove some of them. And it was only in around 2010 that the Warsaw group figured out the minimal basis for SMEFT. Okay. So an example of this would be that, for example, a d equals 6 operator could be, for a scalar, complex scalar field theory, you could have some phi dagger phi cubed over m squared and so on. So this would be an example of a possible dimension 6 operator if there was some scalar theory and there was some new physics scale, capital M. For fermions, you can break fermions up into chirality. So an electron can be written either in terms of left-handed and right-handed electrons, or equivalently by taking the complex conjugate of the right-handed electron, you can use left-handed electron and positron fields. So either one they're equivalent. And so usually when you are doing EFTs with fermions, you break the fields up into left and right-handed pieces, or write everything in terms of left-handed fields, because you have to write down all possible structures, and the Dirac field is including the left and right-handed fields, or these two pieces of the two chiral fields with equal coefficients, and they don't have to be equal. The weak interactions is the chiral theory, where left-handed electrons have weak interactions, and right-handed, well, I mean, they couple to W's, and the right-handed ones don't. So typically in a chiral theory, you want to break the fermions up. Now, if I work with a scalar theory, I have, I'm going to be sloppy about real and complex scalars and so on. You have some m squared phi squared term, and you could have a phi cubed coupling. You could have a phi fourth coupling, and then there's some new physics scale. So in principle, you could have phi fifth over m, phi sixth over m squared, and so on. Now, when you start with an EFT, you kind of not just doing things at random. You know, or I'll put this way, you know already that you have, let's say, a light particle or a light scale, which I'll call little m. So because I'm writing the EFT for the interactions of this object, and then either you know that there's new physics, let's say because you have a BSM theory, or you think there's new physics because you think there's something else, you don't know necessarily what it is. So there's some high scale, I'll call it, which is capital M. And by definition, when you're doing an EFT, these scales have to be separated so you can do an expansion. Otherwise, you can't do the EFT. You have to know what the full theory is and calculate arbitrary functions of little m over big M. But in an EFT where little m is much less than capital M, you're expanding in either little p over big M or equivalently little m over big M, and that's this expansion, okay? You're getting inverse powers of big M here. Now, for scalars, sorry, and so the argument would be that an operator of dimension capital D must have m to the capital D minus 4 in the denominator. So dimension 5 has 1 m, dimension 6 has 2 m's, etc. Okay, so that's so that the Lagrangian has net dimension 4. But if you look at this Lagrangian, okay, so 5 to the 4 has something of order 1, which is consistent with this. But what this should, if you followed this power counting, you would say that m squared phi squared should really be big M squared phi squared. Okay? But it's not, because as I said, the starting point is that I know that there's a light particle with mass little m widely separated from big M. I'm starting from that fact. I'm writing the EFT for this. So you can't have that. So what m squared phi squared is, if I were to write it in this power counting form, is big M squared phi squared times little m over big M squared, just to cancel the big M's. So if you write the mass term as some coefficient times an operator with sort of the naive power counting of m over d minus 4, this coefficient is 2 powers, it's little m over big M squared suppressed. What this means is that phi squared, which is a dimension 2 operator, as far as EFT power counting, it acts like it's dimension 4 because it has an explicit extra 2 powers of suppression. And similarly, the phi cubed operator, if phi cubed has to have a G here, which has dimensions of a mass, and that mass has to be a light mass, so the operator should be some, I don't know, G twiddle little m, where this is dimensionless. The reason is that you can do loop graphs like this and generate a mass squared for the scalar, which is of order G squared, which with this notation would be G twiddle squared M squared. So it has to be of order the light particle scale, otherwise loop graphs are going to make the particle heavy. And so here, phi cubed has an m over m suppression. And so it again acts like dimension 4. So the interesting thing is that this whole, where's it gone? This whole piece here, even though it's written as d less than or equal to 4, is in fact, for power counting purposes, it acts like it's all d equals 4. And this is related to Tuhin's question. We'll come back to this. Okay, so now let's look at scattering amplitudes. So if I have a if I have some scattering amplitude with some bunch of particles, the scattering amplitude behaves in terms of, I'm just going to assume that all momenta on the external legs are of order the same size. It behaves like p to the 4 minus the number of external, okay, let's call it n phi, minus 3 halves n psi. So this is external phi legs, and this is external psi legs. And gauge fields act the same as phis. So for example, a lambda phi fourth interaction, the amplitude goes like lambda, and no momentum dependence because you have 4 external phi fields, and so the 4 minus 4 gives you 0. Now, if I work with contributions from higher dimension operators, you know that I'm getting explicitly 1 over m or 1 over m squared or something from these higher dimension operators. They're there in the amplitude because the coefficient has this m in it. The extra dimension upstairs is made up for in the matrix element by factors of momentum. There might, for example, be an explicit derivative or whatever. So if you look at an amplitude like this, the L d less than or equal to 4 term gives me an amplitude which I can call this p minus n4 minus 3 halves n psi. And then, so this is some basic amplitude. Let's just say it's A0. And then d equals 5 will give me an amplitude which is of order A0 times 1 factor of p over m. Because the coefficient of the d equals 5 operator has an explicit factor of 1 over m, and dimensional analysis is to bring a p. And similarly, a Lagrangian of order d is going to have an amplitude which goes like p over m to the power of d minus 4. Okay, so dimension 6 will be p squared over m squared suppressed relative to the dimension 4 term, etc. Just by dimensional analysis. And if I take a more complicated amplitude, so I'm doing some scattering graph like this, where there's some dimension 6 insertion here and some dimension 6 insertion there or whatever. In general, what's going to happen is every one of these insertions is going to bring down a factor of 1 over m to whatever the operator dimension is. And so the net suppression, so let's say that this is A0 p over m to the n. Here n is d minus 4. That's the suppression factor. If I have a lot of factors like this, the total suppression is the sum of ni, the individual suppressions from each of these vertices, which is the sum of di minus 4. And this is d minus 4. So in other words, inserting a whole bunch of operators gives me an effective operator, an effective power counting suppression, which is related to the sums of d minus 4. Essentially because of the powers of m are shifted relative to the operator dimension by 4. So 2 insertions of L6 will give me this term here will be 2 plus 2 because of this. Well, okay, let's write it. 6 minus 4 plus 6 minus 4, which is 2 plus, I hope I can add, which is 4. And that tells you that this amplitude, 2 insertions of L6, the time-ordered product, or whatever you want to call it, 2L6, is acting like this is a dimension 8 amplitude because it's suppressed by 4 powers. So it comes from a dimension 8 operator, and so on. Okay, so this is the standard. This is what's called the power counting scheme for the EFT, and this is the power counting rule that inserting operators gives you a net result, which is the only thing to remember is the shift by 4. So if I now go, for example, to the standard model, and I look at what, so SMEFT is just L standard model plus L d equals 5 over m plus And the assumption in SMEFT is that the fields are the fields of the standard model. Basically, that's all you're doing. And there is a fundamental Higgs, because the standard model has a fundamental Higgs. So that's here. Higgs effective theory is something where you don't have to necessarily have a fundamental Higgs. There could be some composite mechanism related to chiral perturbation theory. And Tim Cohen will talk about maybe the two and the relation between Higgs effective theory and SMEFT. But here you just assume there's some new physics at a high scale relative to the standard model, and you can write everything in this way. So if you look at the standard model is the most general possible Lagrangian built out of the standard model fields. Every operator that's allowed has been included. And it turns out that in the standard model, baryon number is what's called an accidental symmetry. Which is to say, we never imposed baryon number. We just wrote down all the terms of dimension 4. But then when you write it down, you notice that, oh, by the way, no term has violated baryon number. So this explains, in some sense, why baryon number is such a good quantum number. If the new physics scale, which violates baryon number, is high, you naturally get a suppression over this scale. Now, the first operator which violates baryon number schematically looks like QQQL. That is 3 factors of the quark field and 1 factor of the lepton field. And since fermion fields have dimension 3/2, this is a dimension 6 operator divided by m squared. So this is the first baryon number possible violating term in the SMEFT. It goes like 1 over m squared. Is this clear? So this tells you that if I were to look at proton decay, so P goes to E plus pi 0 or something, where the 3 quarks in the proton are converting into the anti-lepton, etc. The amplitude for that has to go like, the amplitude has to have this 1 over m new physics scale squared. The decay rate is proportional to the square of the amplitude. And so that has to go like 1 over m to the 4th. By dimensions, the decay rate is afforded the energy, and the only energy you have in the problem is the proton mass, because it's the proton which is decaying. So this is m proton to the 5th. And if you're familiar with these 2-body phase spaces, you typically get like a 1 over 8 pi or 1 over 16 pi or something. You can do a slightly improved estimate of the rate by including that. But really, the decay rate goes like the 4th power of the new scale. And if you work out the lifetime, which is 1 over gamma, you find 10 to the 30 years times m gut, or this m, over 10 to the 15 GeV. So in some sense, the proton lifetime is telling you that if there's new physics which violates baryon number, the lowest scale it can be is somewhere 10 to the 15, 10 to the 16 GeV or something, because the lifetime of the proton lifetime, I think, is about 10 to the 34 years now. So this m would, sorry, to the 4th power. Which also is bad news for experimentalists, because if you want to get information on the new physics scale, it's going like the 4th root of the lifetime. So if you want a factor of 10 improvement and a bound on m, you have to do a 4 orders of magnitude improvement in your experimental bound. Now suppose for some reason the new physics, the baryon number violation was dimension 5. As can happen in SUSY if you don't impose certain discrete symmetries. Well, then this 1 over m squared in the amplitude is just a 1 over m. And so now this gets replaced not by the 4th power, but by the square. And this becomes m but this m to the fourth, because it's squared now, this 10 to the 30 years becomes 1 year. So basically, dimension 5 baryon number violation is completely dead, even if your scales were going up to the Planck scale or something, because the 1 over m suppression is too small to make baryon number compatible with experiment. So in some models, you don't get baryon number violation, but you get delta B equals baryon number violated by 2 units as an NN bar neutron anti-neutron oscillations. And the leading operator which does this is, for example, UDD squared, 2 neutrons. And yeah, so that's right. So for example, when you do magnetic moment interactions in low energies, like for the muon, you get muon, sigma mu nu, F mu nu mu. And that is a 1 over m. It's a dimension 5 magnetic moment. But if you work in SMEFT, you won't find an analogous magnetic moment operator at dimension 5. It's a mu bar, sigma mu nu. Well, it's a lepton doublet, sigma mu nu, right-handed muon, F mu nu. Then you need a Higgs field to absorb the SU2 indices. And this becomes dimension 6. And this has some 1 over m squared. And so what happens is that when the Higgs gets a VEV, you generate something like this, but it's now got an extra V over m suppression. This is something like what you're saying, I think. Yeah. So sometimes if you go through some intermediate theory, you can get constraints. Things can be more suppressed than you might have thought because of invariances of the intermediate theory. So again, this is very important for G-2, because if new physics is going through SMEF, then the muon magnetic moment operators which contribute are acting like the dimension 6. But if you had some theory which didn't go through SMEF, as the weak interactions are broken a different way, you could get dimension 5 contributions to G-2, which would also be interesting. Okay, so here, a fermion field is dimension 3/2, and so this is a dimension 9 operator. And so this has got 1 over m to the 5th. And so the amplitude is suppressed by 5 powers of the new physics scale. And you can have models like this with baryon number violations, but provided they're only delta B equals 2, you can have them, m can be much lower than the gut scale, and you're not, it's compatible with experiment. The other example, which is quite relevant, is neutrino masses. So in this standard model, if you just have left-handed neutrinos, you can't write down a gauge invariant mass term. But at dimension 5, you can write down a term which is Higgs lepton doublet. Higgs lepton doublet. Let me not discuss how you contract all the SU2 indices, but this is a dimension 5 operator divided by m. And when the Higgs field gets a VEV, this leads to a neutrino mass, which is of order VEV squared over big M, the electroweak VEV squared over big M. This is basically the seesaw mechanism. If you induce this operator at some high scale capital M, you get a neutrino mass proportional to the electroweak scale divided by big M. So this is an EFT version of the seesaw mechanism. And I put in some numbers. So VEV is 246 GeV, and M, and the neutrino mass I took was 10 to the minus 2 electron volts, then this leads to this seesaw scale of order 6, 10 to the 15 GeV, which is like the gut scale. It's possible that this operator is induced with 2 powers of some gauge coupling squared or the electric charge, or I mean the SU2 coupling squared or something, in which case this would go down a little bit. But the seesaw mechanism and the size of neutrino masses is pointing to some high scale seesaw. But maybe the most important thing from this is that in the standard model, if you don't have explicit right-handed neutrino fields and you want this operator to produce neutrino masses, this operator violates lepton number by 2 units because it's got the lepton doublet and the lepton doublet, not its Hermitian conjugate. So a consequence of this is that neutrino masses, m nu violates neutrino lepton number. And so you should see neutrinoless double beta decay. So I think that's called beta, beta 0 nu. Neutrinoless double beta decay. So double beta decay would produce electron, neutrino, some isotope, some nucleus goes to A prime plus. It's like 2 simultaneous weak interactions, but when the presence of this Majorana mass, you can pair off these 2 with a mass term, and so you can have A prime plus electron. And so people are looking for that, but clearly measuring this would be very important because it would confirm that these ideas are right in the sense that we expect that the neutrino mass is lepton number violating, and you should be able to measure this. And they're doing lots of experiments, but unfortunately from the neutrino oscillation experiments, we don't really know what the neutrino mass matrix, the electron entry, we don't know what that is. We know some constraint about linear combinations of masses. And so it's not a direct comparison, but people are getting sensitive to numbers in here comparable to the known neutrino masses. Okay, so let me now discuss one example of what's called a matching condition, but at tree level, just so you get some sense of what's done. So this is the weak interactions, so the low energy weak interaction. So for example, I could look at B to C E nu. So the Feynman diagram for that is B to C, mu to E via W exchange. So what is the amplitude for this process? Well, each vertex is minus Ig. G is just the SU2 gauge coupling, minus Ig over root 2. If I write down the Feynman rules, there's minus I for each vertex. So that it's squared because there are 2 of them. Then the upper line, I could either do spinors, but I'll do it in terms of fields. You get a C bar, gamma mu, P left B. On the lower line, you get E bar, gamma nu, P left mu E. Because this is a B to C transition, you get a VCB factor here from the coupling constant. And then you get the W propagator, which is minus I G mu nu over K squared minus MW squared, where K is the momentum flowing through here. And the point is that if I'm applying this for B decays, and the B is decaying into a C quark, K, which is the momentum of the C minus the momentum of the B in the kinematics of B decays, is constrained to be some number of order mb, because that's the only energy you have. It's a B quark at rest, and so k is small, so k squared is small compared to mw squared. And so in this sense, at tree level, these EFTs are basically the same as doing just a Taylor series expansion. So the only expansion is really in this propagator. So I'm going to flip its sign and write 1 over mw squared minus k squared, and that's 1 over mw squared times 1 plus k squared over mw squared plus k fourth over mw fourth, and so on. So this first term, the one term, will give me a dimension 6 operator. The next term will have the factors of k squared, will be 2 extra derivatives, will be a dimension 8 operator, and so on. And if I look at just the dimension 6 part, then the way this is usually written is minus 4g Fermi over root 2 VCB C bar gamma mu P left B E bar gamma mu P left mu. Okay, the 4g Fermi over root 2 is for historical reasons as to how these operators were normalized in the Fermi theory of weak interactions. But the standard model tells you what G Fermi is, because it's this G squared over 2. And then there's a 1 over mw squared. And so 4g Fermi over root 2, which is the coefficient, is G squared over 2. Sorry, G squared over 2 mw squared. Okay, and the sign works out to be minus because of the I squared. And this minus I, because this is the diagram, so the Lagrangian, I have to drop a factor of I to get to the Lagrangian from the amplitude. So let's say this is the amplitude. And mw in the standard model is gv over 2. So this is 2 over the Vev squared. So we have a prediction for Fermi's constant in terms of the Vev. But it's also important to note that this Fermi constant is only sensitive to V. And so historically, from mu decays, which is a very similar process, you can get G Fermi and you can get V. But you don't know what the W mass is, because the W mass depends on this extra coupling G. And so people didn't know what the W and Z masses were. And then eventually, the electroweak coupling constants were measured from parity violating scattering. And then once you know both G and V, then you know what the W mass should be and so on. So that's how the W mass was determined. Through experimental data before it was actually found. So the experimentalists knew how to find it. Okay, but now once we have this, we have now a local Lagrangian. So this has been turned into a 4 Fermi operator, and there is no scale MW anymore. It's been removed because this Lagrangian has no propagating W's or anything else. I can now take this operator and I can calculate the rate for B. I'm just going to do it to the parton level, B to C E nu, and it gives you VCB squared. Okay, if you haven't done this ever, you should at least do the muon decay version of this. Then you get a function which I'll call function of rho. Rho is MC squared over MB squared, and F of rho is 1 minus 8 rho plus 8 rho cubed minus rho fourth minus 12 rho squared log rho. Okay, so what has happened is when we calculate this decay rate, it's a function of MB, MC, MW, and just pretend the electron is massless. By going to the EFT, we have treated MW as large That is, we have dropped MB over MW and MC over MW terms. We're treating it as, and MB and MC are EFT parameters. So we have two scales in the EFT, MB and MC. We have one scale in the original, in the high energy theory. So one additional scale, which is much larger. So we're dropping ratios of MB and MW and MC over MW. But the EFT contains the full dependence on IR scales, on, in this case, MC over MB. And when you calculate the phase space integrals, you get this whole function and so on. There is no expansion being done in the ratio of MC over MB. And now you can go to high order, so you could put in gluons across here, and then gluons here, and so on, and sum the leading logs and all of this other technology, which I won't have time to discuss. But for example, in this case, the QCD corrections, which are given by doing the renormalization group running of this operator from the weak scale, so from mu equals MW down to mu equals MB, change the coefficients by order 1. That is, it's about a factor of 2 change in the coefficient. So there's no sense in which these QCD radiative corrections are small. And that's because of what I mentioned in the first lecture. These corrections go like alpha logs, and the logs compensate for the alpha, and you get an order 1 shift, and you have to do RG improvement. Okay, but so maybe some of the other lecturers will discuss this in more detail. So the last point I want to make, which is, how do you do loop corrections? So suppose I had some loop calculation where I have 2 dimension 6 operators, and I do some loop, and I get a 5/4 interaction. I get some kind of loop d4k over 2 pi to the 4th. There will be some 1 over k to the 4th from these 2 propagators. But now a standard lambda 5/4 coupling is just lambda. Here I have a dimension 6 coupling, so that's 2 powers of momentum higher. So I'm going to get some k to the 4th type thing from the vertex factors because it's a dimension 6. And because it's a dimension 6, I get 2 factors of 1 over m squared. So I get something like this. Now, if you're used to thinking about EFTs with cutoffs, you're in big trouble, because if you think of this thing as 1 over m squared squared times the integral d4k over 2 pi 4th, 0 to a cutoff, you're going to get cutoff to the 4th over m to the 4th. And the EFT is valid until some scale of order m. And so this lambda is of order m, and this is order 1. And your whole loop expansion and everything else just completely breaks down. And really, you cannot use momentum space cutoffs to think about EFTs. The entire power counting breaks down, and the whole EFT expansion breaks down. And historically, the momentum space cutoff also broke gauge invariance, and so people abandoned it a long time ago. So the only renormalization scheme which is consistent with the EFT power counting is to use dimensional regularization. And in dimensional regularization, if you do a loop integral, so I'm just going to d to the dk over 2 pi, just going to write down a standard integral k squared to the a over k squared minus m squared to the b. And here you have a mu to the 2 epsilon. That gives you something which is I over 4 pi to the d over 2, mu to the 2 epsilon, gamma A. Well, maybe I shouldn't have wasted my time writing this, but E minus A. Whatever. Okay. So the details of this integral are not relevant, really. What's happening is the only scale which the integral depends on is m. And what is m? M is a scale in the denominator. If you have multiple propagators, you can use a Feynman parameterization to turn it into some m. So these scales are coming from the propagators, which means they're the masses in the EFT. Or if you had momentum flowing through the vertex, you might get, if you do one loop diagram, you get something like p squared x1 minus x plus m squared or whatever. So this is masses and momenta in the EFT. So these are all small scales that you get here. There is no capital M, which is our big scale. There is no capital M. Mu is the mu of dimensional regularization, but it always comes in as this fractional powers, mu to the epsilons from the coupling constants. And so when you expand this out, the mu only enters through logs of mu. There are no powers of mu. Yeah. This is small m. That is small m. It's the same m as here. So there is no capital M anywhere in here, is what I'm trying to say. It just can't occur because it's nowhere in the integral and there's no cutoff. You're doing dim reg and you're putting in the little mu and the mu, so it never occurs. So the statement is that we have what you might call manifest power counting. That is, the loops also give you the same power counting as before. So this graph with two L6 insertions behaves like 1 over m to the fourth. And the fact that there's a loop is irrelevant. It's still 1 over m to the fourth even when you do the loop. And it can be corrected by logs of mu over light scales. Basically, there are no heavy scales anywhere except explicitly in the coefficients where there's some power of m, and that's the only place where m's occur. So one of the consequences of this, which is very helpful, is that what are called scaleless integrals vanish. So integrals like d4k over 2 pi to the fourth is 0. Why? Because it's like one of these integrals where m squared has been set to 0, and there's some value for here. B is 0, m squared is 0, and b is 0, and a is 1 or something. But when you take m squared to 0 in dimensional regularization, this thing is a fractional power. And the rule is that m squared to something with the fractional power goes to 0 as m squared goes to 0. In dim reg, you throw away anything with fractional. You assume that the dimension or the epsilon is such that this has a finite limit, and the finite limit 0 as m squared goes to 0. In some sense, that's the definition of dimensional regularization. Second, there are no power divergences. So you cannot ever get m to any positive power. You only have log divergent integrals. So you can get logs of mu. And the logs of mu are related to 1 over epsilons in doing the diagram, and the 1 over epsilons are related to counterterms in anomalous dimensions. So that's why you can sum the log mu's with the renormalization group. Okay, so the formula we had, which was that the net n, the net power suppression n, is the sum of ni, which is the sum of bi minus 4, is also valid for loops. So our EFT has a double expansion. One is an expansion in powers of 1 over m. And we have a loop, assuming perturbation theory is valid, we have a loop expansion as well. And they're consistent with each other. That is, you can read off the powers explicitly, and then you can read off the loops, or you can work to some fixed number of loops and do the calculation. Okay, so now let's look at this issue with Tuhin's question. So now if I take lambda h dagger h squared and look at some diagram like this, and I calculate the loop in dimensional regularization, I'm going to get an operator which is h dagger h, because those are the external fields. This integral is the integral which is d4k over k squared minus m squared. So it's order k squared. It's an order dimension 2 integral. But the only mass which can enter is the mass in the propagator, which is the Higgs mass. So this gives me something which is order m Higgs squared log m Higgs squared over mu squared. Okay, so the standard argument which people use is that this diagram gives me cutoff squared some log. And so there's a correction to the Higgs mass, which is of order the cutoff squared. And this is supposed to be the hierarchy problem. But look in Peskin and Schroeder, I think there's a problem. Do this diagram. Okay, you won't get cutoff squared in dim reg, you just get m Higgs squared. So the way this is phrased is completely misleading. If you have a consistent EFT, so you have a unified theory with some scale m gut, which is high, and the weak scale, which is low, and my Higgs mass is of order the weak scale, I'm starting with a theory where I know that I have a light Higgs. My Higgs is not at the gut scale, because otherwise I wouldn't have the standard model. It's perfectly stable under radiative corrections if you do them properly. The physics question is, why did your theory have 2 scales? But that's a different problem. All of this stuff of fine-tuning and doing things order by order and stuff is, I think, is just completely misleading. The question is, why is the physical Higgs mass light and the physical, whatever the gut scale boson have? There are 2 scales. But I don't see any reason why a theory can't have 2 scales. I mean, why should all scales be the same? So this is like this is a different kind of problem. It's a physics problem to explain why you can widely separate 2 scales. But it's certainly, I don't think it's anything like the way it's always presented in the talks at all. I think that's just misleading. So I think since we want to have lunch anyway, I will stop here. Maybe I'll just make one other point because of this formula, which is just that if I, sure. I know, but I can't calculate with, I mean, so I hear the words, right? But you will see from any of the lectures, not one person is going to calculate with a Wilsonian effective action, right? So what use is it? So in the lattice, you have this problem. So in the lattice, you get power divergences proportional to lattice spacing squared. Or what? Because this is the analog of, sorry, the other way, whatever. The cutoff is 1 over the lattice spacing. So there'll be like 1 over a squared. And then you have to do a lot of fine tuning to try and, so if you use Wilson fermions, for example, where you break the chiral symmetry, you have to now do a lot of fine tuning to make sure that the physical pion is light or whatever. But we don't say that that means QCD is wrong or something. It just means, you're using a computational scheme and the way you set it up There's some hard work you need to do, but it's not a fundamental problem. Wait, if you have a, what kind of a state? Okay, but the problem is going to be that you can't make that fermion too heavy, right? Because yeah, but no, but that has a singlet mass. So that's why there yeah, so you have L bar nu Higgs, some YE, and then you have a, I guess you got to do N bar nu Higgs, whatever, Y nu, and then you have NN with no Higgs and an M, a big M, right? And then you integrate, that's how that operator, I don't know if it's still there, is generated. You now integrate out capital N and you generate some 1 over M type thing, which goes like Higgs squared, lepton squared. What am I doing? This is garbage. It's L bar N. Something like this. No, that's right. Yeah. No, is the scalar heavy or light? Okay, the scalar is, yeah, 100, yeah. Yes. Yes. Yeah. Yeah, so you're going to get, you're talking about matching, one loop matching, you would get one loop matching corrections. So yeah, so the PDG, the only MS bar masses they quote, I believe, are for the quarks.
That's okay.
No, but it's important because an MS bar, I didn't say this, but okay, since you bring it up. So the MS bar masses are not physical observables. So nothing changes. That's right.
But I write, if I want to write an MS bar masses, when I see that I have to bring in the mass of that.
Okay, so here's this, okay, so let's call this M heavy, right? Here's a theory with M light, M and M heavy. And now down here, I only have the light scalar. And this is your fermion, right? So what you're going to find is that, let's call this M minus and M plus or something, the low energy theory and the high energy theory, right? M minus squared is like M plus squared. And then you're going to get some 1 over 16 pi squared M heavy squared something. That's what you're worrying about, right?
Yes. Consequence of that is the question is, I expect that, the people say, I think they expect that the heavy, you couple to heavy physics, your mass expected the heavy things come from that.
Yeah, but I would think of it as, yeah, so that's why I'm trying to say that the parameters in the Lagrangian, which are these, are not the relevant things. What you want to do is the physical parameters. And the physical parameters are the pole mass of this and the pole mass of the other one, and one is big and one is small. And then this relation does whatever it needs to do to make sure that's correct. So it's a question of whether you think somehow that these parameters in your Lagrangian, which depends on the scheme and so on, mean something, or the physical. Yeah.
I think that's the way.
That's fine, yeah. I mean, which is, I mean, so that, I call that, I think of it as a different way, but yeah, you have, your theory had two physical parameters in it and one is lighter than the other. And you can either say, I don't understand it, I just look at it from experiment and I put them in. But if you are hoping to understand it from a more fundamental theory, then your new fundamental theory has to produce these two eigenvalues, which are very different from each other. But I think the kind of thing you might do to solve that problem, I think is different than, I don't know. I mean, how you think about it might matter into how you approach solving the problem. We haven't solved it anyway, so yeah. But certainly all these ideas of naturalness predicted all sorts of, I mean, I've been listening to this since I was an undergrad, and not one thing has worked out so far, right? So it's been a long time. So I don't know what to do with it. Whereas EFT is done the way I have, is lots, you know, there's a lot of the PDG depends on all of these calculations. But so I think it's where you want to spend your time, in some sense. Yeah. Yeah. Yeah.
Have one light particle and one heavy particle in the loop as well, right? And then from that diagram, you could get the one loop corrections to the vertex to
Yeah.
this.
So I don't have time to do any of that. So this is discussed in the Jesus lectures, an explicit matching calculation where there's a where you have like one heavy and one light, some diagram like this, leading to some, I forget, you know, some interaction like this where there's a heavy light mixed diagram and how to take that into account in the matching.
So my question is, in that case, you would again, face this problem of, within log you will have both the light mass and the heavy mass sitting.
Yeah, so what you're doing here is if you have a light mass and a heavy mass, you're expanding in light little m, because by assumption little m is small. So when you have this propagator, 1 over k squared minus m squared, you expand that as 1 over k squared plus m squared over k fourth and so on. And then you can do the loop order by order, and the loops are going to give me some log mu squared over heavy mass squared, and then m squared log mu squared over heavy mass squared, and probably with a, with a 1 over m squared here and so on.
Okay.
So sorry, so this would be m squared, or whatever. Anyway, let's say times 1. So you'll get an expansion in little m over big M and logs of mu over big M is what you get.
Yeah, okay.
So effectively, you can do the matching by setting all the IR scales to 0. So in some sense, you set little m's to 0 inside all the loops. So the logs don't involve it. And so I can explain it. It's in the Jesus lectures, there's an explicit calculation of this. And, but as I said, I had like 6 lectures. So
Thank you.
we can talk over dinner or whatever, lunch. Yeah.
M.
Yeah.
So is there any implicit assumption that the scaling dimension of the operators, the actual scaling dimension is almost equal to the canonical dimensions on, like, can it change the Wilson coefficient in such a way that we get large corrections and it's not order 1 Wilson coefficient?
Yeah, so effectively here we're doing things in perturbation theory. And so there will be anomalous dimensions, but they're perturbative. And you can run, and you get coefficients which are modified by large amounts, like in the weak interactions or in the gut problem, the coefficients could be multiplied by 5 or something. But it's not like we have some non-perturbative fixed point, which is taking a dimension 3 operator and making it dimension 2 or something. So
So
Because then you can't actually go calculate in perturbation theory. So in some sense, I don't want to say I'm doing perturbative EFTs because chiral perturbation theory and HQET and stuff have non-perturbative physics as well. But the places where you actually calculate diagrams, we're assuming those diagrams can be done in perturbation theory.
yeah, so it can't be that the dimension 6 operator scaling dimension becomes, let's say, dimension 2 or something.
No,
Okay.
not in these cases. Yeah.
Oh, thank you.